Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 19, Galileo and Kepler. In our last lecture, we met Nicholas Copernicus, who proposed that the sun was the center of the solar system and, in fact, the center of the universe, as opposed to the Earth. It was simpler in concept, but didn't do a better job of predicting the positions of the planets in the sky. So we also met Tycho Brahe, who understood that both Ptolemy and Copernicus didn't have good models for predicting where the planets would be, and decided that the best way to go about developing a model like that would be to observe very carefully, very accurately, the positions of the planets in the sky for over 2 decades. In this lecture, we're going to meet Galileo and Kepler, who both made significant contributions to our understanding of how the universe works and how our solar system is laid out. So let's meet Galileo first of all. He was born in 1564 and died in 1642. Galileo is often credited with inventing the telescope, and he did not. The telescope may have been invented by a Dutch lensmaker by the name of Hans Lippershey in 1608, but really what happened was Hans Lippershey filed a patent for a telescope in 1608. The telescope itself may have existed longer before that. So Galileo did not invent the telescope. He was also not the first person to use the telescope to look at the sky. For example, an English astronomer by the name of Thomas Harriot looked at the moon in July of 1609. So what is Galileo famous for? Galileo, though he did not invent the telescope and wasn't the first one to use the telescope to look at the sky, he was the first person to use a telescope to study the sky systematically, to record what he saw, to explain what he saw, and to publish his results. That's why Galileo is famous. Galileo is famous because he not only looked at objects in the sky through his telescope, but he tried to understand them, and he wrote those explanations down, and he disseminated those observations, much like a modern scientist. One of Galileo's treatises is known as Sidereus Nuncius, or the Sidereal Messenger. And in the Sidereal Messenger, Galileo reports that the moon has mountains and valleys. It was not a perfect world. Aristotle, you'll remember, had taught us that the universe, that the sky, I should say, was made of material that wasn't found on Earth, called ether, and that the objects in the heavens were perfect and unchanging. And yet, when Galileo looked at the moon through a telescope, he saw things that looked very much like large mountain ranges. He saw things that looked like valleys. He certainly saw craters on the moon, may not have understood what they were, but he saw that the moon was not a perfect body. In fact, it was very much in some ways like the Earth, having mountains on it. And that went against what Aristotle had said. Galileo also noticed that our Milky Way galaxy was made up of individual stars. The Milky Way looks like this milky band of light cutting across the sky. But when you look at it through a telescope, even a small telescope, it breaks down into billions of individual stars. Galileo observed the planet Jupiter with his telescope, and he noticed that Jupiter had 4 companion moons that we now call the Galilean moons: Io, Europa, Ganymede, and Callisto. The Galilean moons are Jupiter's 4 largest moons. And Galileo watched Jupiter night after night, and he could see the moons orbiting or moving around Jupiter. This is a page from Galileo's notebook, and in there you can see Jupiter drawn as the largest planet, and then the little stars next to it represent the moons, and you can see that night after night after night after night, the moons were moving around. And Galileo understood that they were orbiting Jupiter. And this was important. This was a very important piece of evidence. And the reason this was an important piece of evidence is one of the arguments against the Earth orbiting the sun was that if the Earth orbited the sun, it would just leave the moon behind. Why would the moon continue to orbit the Earth if the Earth was moving? Well, what Galileo said is, here is an example of an object that is undoubtedly moving. No one doubted that Jupiter was moving. Whether you believed it was orbiting the Earth or orbiting the sun, it was moving in either case. And here were the moons, clearly orbiting around Jupiter and keeping up with Jupiter as it clearly moved through the sky. So what that indicated to Galileo is that it was certainly possible for the Earth to orbit the sun and not leave our moon behind. Galileo also discovered sunspots. Now, sunspots are magnetic storms on the surface of the sun. They are places where the magnetic field allows a little patch of the sun's surface to cool off, but it prevents new hot gas from getting in there to warm it back up again. And because those patches are somewhat cooler than the rest of the surface of the sun, they look a bit dimmer. They look like these little black spots on the sun. But Galileo noticed that, like the moon, the sun was not perfect. And he also noticed that it rotated. He watched the sunspots day after day, and as he watched these sunspots, he could see the sun rotating. Now, unfortunately, Galileo did not have the fancy solar filters that we have today, and a lifetime of observing the sun meant that late in life, Galileo developed cataracts, and he went blind. He could no longer see, and that was probably in part due to his observations of the sun, using only very, very crude smoked glass instead of proper solar filters as we would today. And one of Galileo's most important observations was that Venus goes through phases. This is a fantastic series of photographs that were taken in 2002 by an amateur astronomer of Venus as it orbits the sun. So the sun is down here at the center, but obviously it's not captured in the same photograph. And as Venus orbits the sun, you can see that it goes through a full set of phases. Now, some of the phases are missing from this diagram. And I will also point out that the photographer only photographed half of it, and I flipped it over to make the second half over here. Just so you can see the full cycle of Venus going through all of its phases. So what's going on here is the sun is at the center of the solar system. Venus is orbiting around the sun. When Venus is on the very far side of the sun, we would see it in the full phase. But we can never see Venus like that because it's so close to the sun that we don't see it. But Venus does go through a gibbous phase, a half phase, a crescent phase. Interestingly, with Venus, we call it a half phase. We don't call it a quarter phase because the quarter phase with the moon refers to the fact that it's 1/4 or 3/4 of the way through its phases. So there Venus looks half, and it goes through the crescent. And then, of course, there would be a new Venus here. But again, because it's so close to the sun, typically we can't see it. So this is a schematic of what's going on. That's an actual set of photographs of Venus going through its phases. So why were Venus's phases so important? Well, I want you to answer this question in learning catalytics. So here's our first learning catalytics question of the day. Can Ptolemy's model of the solar system account for Galileo's observation that Venus goes through phases? Yes, no, or possibly. Let me describe what's going on. Remember, in Ptolemy's model, the Earth is sitting still at the center of the universe. The planets are orbiting on epicycles, and those epicycles are orbiting the Earth on a deferent. So Venus is going around its epicycle right here, and that epicycle is getting carried forward along a deferent. The sun is also traveling around the Earth on a deferent right here. In fact, it's traveling on an epicycle on a deferent right there. The question is, what phases will Venus show? Does Ptolemy's model allow Venus to go through all of its phases, or thinking about Venus here going around its little epicycle right there, does Venus not demonstrate all of the phases? So think about what will happen here. Go ahead to Learning Catalytics and answer this question. All right, welcome back. So what did you come up with for an answer? The answer to this one is, as Venus goes around its epicycle here, the far side of Venus, the side that's facing away from us, always faces the sun, which means Venus will always look to us to be crescent or new. We will never see a full Venus. We'll never see a gibbous Venus in this case. Venus will always appear as a crescent or as new right there. So this was evidence. Galileo's observation that Venus goes through phases directly disproved Ptolemy's model for the universe. It proved that Ptolemy's model was not right, that planets are not orbiting on epicycles, that are orbiting on deferents around the Earth. The question is, did it prove Tycho Brahe's model wrong? So now I want you to think about Tycho Brahe's model. And in Brahe's model, Venus is orbiting the sun, and the sun is orbiting the Earth. Does that does Venus in that case go through a full set of phases? So again, go out to Learning Catalytics, spend a few seconds, answer this question. All right, welcome back. So what did you get this time? What's interesting about Tycho Brahe's model is because Venus is orbiting the sun and the sun is orbiting the earth and the earth is sitting still, Venus can be on the far side of the sun and appear full to us. Venus can be on farther from the sun than the earth is, Venus can be farther from the earth than the sun is, and we can see the gibbous phases, but it will also come in between and we will see the crescent phases and the new phase. So in fact, in Tycho Brahe's model, Venus goes through all of its phases, just like we observe. So although we can use Galileo's observation of the phases of Venus to rule out Ptolemy's model, we can't use it to rule out Tycho Brahe's model. Now here's the thing. Tycho Brahe's model wasn't taken very seriously just because it was so complicated with everything orbiting the sun and then the sun orbiting the earth. But in any case, Tycho Brahe's model is consistent with Galileo's observation that Venus goes through its full set of phases, as was Copernicus's model. And it's a really interesting point that sometimes in science, two models can explain something equally well, and you'll need more evidence to prove which one is true. Well, in 1632, Galileo publishes a significant work. It's called The Dialogue Concerning the Two Chief World Systems. There are three characters in this book. One of them represents Galileo himself, and he argues for the Copernican model, the heliocentric model of the solar system. There's a neutral third party that listens to the arguments of the other two parties, and then the third party is a man by the name of Simplicio, in essence, a simpleton, and he believes Aristotle's view of the universe with the earth sitting still at the center. And throughout a series of lectures over 4 days, Galileo's character lays out the evidence for the heliocentric system, the Copernican model, with the sun at the center of the solar system and the earth orbiting around the sun. As you can imagine, this was quite controversial. We talked in the last lecture that Copernicus's model with the sun at the center and the earth going around removed the earth from a special place. It removed the earth from the center of the universe. Copernicus never felt the repercussions of this because his book wasn't published until he was on his deathbed. But now Galileo comes along and he publishes a book that specifically argues for the Copernican model. On top of that, some people have argued that Simplicio was modeled on the Pope, or at least some important philosophers that were important to the Catholic Church at the time. So it seems as if Galileo went out of his way to antagonize the Catholic Church. In the end, the book was banned by the Inquisition. Galileo had to recant his errors, and he was placed under house arrest, and he spent the rest of his life under house arrest until 1642. Now, in addition to astronomy, Galileo also studied physics and mechanics. He studied the physics of motion. Aristotle had said, basically, that an object in motion will come to rest, and an object at rest will remain at rest, that the natural state of things is to be at rest. But what Galileo realized is that the opposite, or well, part of that is true. An object at rest will remain at rest. But Galileo came to realize that an object in motion will remain in motion unless it's acted upon by a force. Galileo also noticed that things fall at the same rate regardless of composition. Galileo predicted, or Galileo's laws predicted, that if we had feathers and an iron ball, and we took them to the top of, say, the Leaning Tower of Pisa, which Galileo probably never did, and dropped the two of them, in the absence of air resistance, they will both hit the ground at the same time. Now, because of air resistance, of course, the feathers will float down, but with no air resistance, both of them will hit the ground at the same time. Galileo determined this actually from rolling different things down a plane, an inclined plane. And then finally, Galileo came up with the idea that motion is relative. If everything is moving together, there's no indication of motion. We've seen this with the rotation of the Earth, the fact that you and I don't notice that the Earth is rotating because everything is rotating with us. When everything is rotating with us, there's no indication of motion. And he published all these results in something called the Discourses on Two New Sciences. So those are Galileo's major contributions. But what Galileo really laid the foundation for was the adoption of the Copernican model. Here was observational evidence that Ptolemy's model did not work, and that there was a better explanation for what was going on in the universe and how the solar system was put together. The next astronomer that we're going to meet is Johann Kepler, and he's probably the most important of the astronomers that we're meeting right now. So you might remember that Kepler was a young mathematician, and he was hired by Tycho Brahe. Tycho Brahe wanted to work out a model of how all the planets were moving in the solar system, how they were all orbiting the sun, which was orbiting the Earth, you'll remember, in Brahe's system. The problem was the mathematics was beyond Brahe. He needed to hire a mathematician to do it. Well, in 1596, Brahe was forced to leave Uraniborg, that observatory he had built on the island of Hven. So the king, who was sponsoring Tycho Brahe, passed away, and the resulting monarch was not a supporter of Tycho Brahe. So he had to relocate to Prague in 1596. He'd had all his data, he had all of his observations, and now he needed to put it together in an explanation for how the planets orbit around the sun. But as I said, the mathematics was too difficult for him. So in 1600, he hires Johann Kepler to help him model the motions of the planets. And in particular, he understood that Mars was the one that was hardest to understand. And so he started with Mars. The problem is Brahe wanted to make sure that Brahe got credit for this new model. And he especially wanted to make sure that somebody like Kepler, who he hired on just to do the mathematics, did not get credit for this. So to make sure that Kepler couldn't figure it out before he did, Brahe fed small amounts of data to Kepler. Kepler really wanted to see the whole orbit of Mars. He wanted to see the whole big picture, but Brahe wouldn't let him. Brahe would give him some observations and ask Kepler to analyze the observations and then give him back, and give him some more observations and give him back, and give him more data and give it back. Kepler felt that he really needed to see the whole sweep of observations to really understand what was going on. So, in an event that's particularly important in the history of astronomy, Tycho Brahe dies unexpectedly. So the story that's been passed around for years, but it's not true, is that Brahe was at a dinner, and at that dinner everyone was drinking, and various stories say that there was a prince at the table, or the king was at the table, and that you were not allowed to get up while the prince or the king was at the table. And Brahe was drinking so much that he had to urinate, but he wasn't allowed. It would have been rude to get up and leave to go urinate, so he just had to hold it, and he held it long enough that his bladder burst. Turns out that's probably not true. More likely than not, Tycho Brahe died of a simple bladder infection. The fact that they didn't have antibiotics back then. Interestingly, Tycho Brahe was also an alchemist. He was trying to figure out how to turn various elements into gold, and he experimented with many of these. And he also experimented with many of these elements as medicines. Years later, centuries later, when Tycho Brahe's body was dug up and was analyzed, it was found to contain a significant amount of mercury. And that was either from his alchemist experiments of trying to turn base metals into gold, or it came from treatments that he himself was administering for his bladder infection. So he may have been taking mercury for his bladder infection. In any case, Brahe dies unexpectedly. And Kepler is able to steal the notebooks that contain all of Brahe's observations, all of his detailed records on the position of Mars. Now, Brahe's family sues Kepler to get the books back, but in the meantime, Kepler uses the data to discover the true nature of the orbit of Mars and the true nature of the orbits of all the planets in our solar system, and he publishes the results in 1609 in a book called The New Astronomy, or Astronomia Nova. Kepler derived 3 laws of planetary motion. You'll remember that what Copernicus said was that everything was going around the sun, but Copernicus believed in Aristotle's view that everything orbited on perfect circles. What Kepler discovered is that things are not orbiting the sun on circles. They're orbiting the sun on ellipses. And that is Kepler's first law. Now, we're going to go over the first law here. I'll come back to this slide when we do the second and third laws. So don't worry about losing the rest of the slide. So let's do the first law. Each planet moves about the sun in an orbit that is an ellipse, with the sun at one focus of the ellipse. So this is how you draw an ellipse. Take two pins, put them in a piece of cardboard, connect them with a string, put a pencil inside the string and pull it taut, and then just move the pencil in a motion. And if you keep the pencil taut, it will trace out an ellipse. For those of you that you remember your high school geometry, an ellipse is defined as the set of points for which the distance from two focal points is a constant. So we add up this distance plus that distance from that focal point, and it is a constant as you sweep around those two pins. So just real quick, some numbers about an ellipse. We call the large axis right here, the large axis of the ellipse is called the major axis. It's the widest diameter of the ellipse. And the minor axis is the shortest distance across the ellipse. So that is the minor axis and the major axis. In astronomy, we often talk about the semi-major axis, and the semi-major axis is simply the major axis divided in two. It is half of the major axis. It's kind of like the diameter and the radius of a circle. The radius of a circle is half the diameter. The semi-major axis is half of the major axis of an ellipse. Now, the semi-major axis, so here's the things I've been stating already. The major axis is the widest diameter. The semi-major axis is half of that. Turns out that the semi-major axis is also the average distance of the planet from the sun. Imagine that we have, and I should have mentioned, I'll say this right now, is that what Kepler said here is that each planet moves about the sun in an orbit that is an ellipse with the sun at one focus of the ellipse. Each of these pins represents a focus of the ellipse, and the sun is sitting at one focus and the other focus is empty. So as the planet orbits the sun on an ellipse, the sun sits at one focus, the other focus is empty. All right, so the average distance, so let's talk about the average distance that a planet has from the sun. The average distance is simply the maximum distance from the sun plus the minimum distance from the sun divided by 2, right? The average is the minimum plus the maximum divided by 2. Well, the minimum plus the maximum turns out to be the major axis, right? The maximum distance plus the minimum distance is just the major axis. So, and then if we take that major axis and divide it by 2, we get the semi-major axis. And that means that the semi-major axis is the average distance from the body to the sun. So that is the reason you'll see throughout the rest of our lectures, when we talk about elliptical orbits, we always use the semi-major axis. It turns out it is also the average distance that a planet has from the sun. And again, to go over that, the semi-major axis is just the major axis divided by 2. Well, the average distance from the sun is the maximum distance plus the minimum distance divided by 2. That's how you take an average, the minimum plus the maximum divided by 2. Well, the minimum plus the maximum distance from the sun, remember the planet is on this elliptical orbit right here, so this is its maximum distance from the sun. This is its minimum distance from the sun right here as it moves on its elliptical orbit. The maximum distance plus the minimum distance is just the major axis. To get the average, we divide that by 2, but the major axis divided by 2 is also the semi-major axis, and so the semi-major axis is the average distance. All right. We use a number to describe the ellipticity of an ellipse, that is how squished the ellipse is, and we call that number the eccentricity. The eccentricity is a measure of the roundness of an ellipse. The eccentricity of 0.000, an eccentricity of exactly 0, is a perfect circle. And an eccentricity near 1 is a very elongated ellipse. So let's look at some eccentricities here. Here are some example eccentricities. Here's a circle with an eccentricity that is exactly 0. And that means that everything is equidistant from the center. Okay, and we would call an ellipse with an eccentricity of 0 a circle. So a circle is a special kind of ellipse, or a better way to put it is all circles are ellipses, but not all ellipses are circles. Here is an ellipse with an eccentricity of 0.3. So now we can see the two individual focal points. The sun sits at 1, and then the planet orbits around. The other focal point is empty. Here's an eccentricity of 0.5, an eccentricity of 0.7, and an eccentricity of 0.96. So you can see the higher the number gets, the more squished the ellipse gets. So looking at these figures for a second, I want you to make an estimate for what the eccentricity of the Earth's orbit around the sun is. So one of these numbers is the eccentricity of the Earth's orbit around the sun. Is the eccentricity of the Earth's orbit around the sun 0.0000, 0.167, 0.3333, 0.5634, 0.9166, or is it 1.0000? So go ahead and go out to Learning Catalytics and answer this question. Okay, welcome back. So how can you answer this question? This is one that I want you to go back and think about what we said during the seasons. I said during the seasons that the Earth's orbit around the sun is elliptical, but it is so close to a perfect circle that you can't tell the difference. Well, it's not a perfect circle, so that means that the eccentricity is not 0. So it's not A. But it's also not going to be as high as 0.333, because with an eccentricity of 0.3, you can clearly see that that is not a perfect circle. You can clearly see that that is an elliptical orbit. And these are even more elliptical than that one. So the only answer that works out here by the process of elimination is 0.0167. Now, another neat thing about the eccentricity here is it tells us how much closer the planet is at its closest and how much farther than average it is. So when the Earth is closer to the sun, in its annual orbit around the sun. So when we're closest to the sun in January, we are 0.0167 closer. In other words, we're 1.67% closer than average. And when we are at our farthest from the sun in July, we're 1.67% farther than average. So that eccentricity is kind of useful that way. It tells you how much closer or farther than average you are if you turn it into a percent. Okay? So, and you can imagine, as we said with the seasons, the total change then in distance from when we are closer to the sun to farther from the sun is about 3.4%. That is, when we are closest to the sun, we're about 3.4% closer than when we are farthest from the sun. And as you can imagine, changing the distance to the sun by just 3% is not going to explain the difference between a hot summer day and a cold winter day. Now, most of the planets in our solar system orbit the sun on ellipses that have very low eccentricities. Some of the planets have higher eccentricities, like Mars. So Mars here, you'll notice the eccentricity of Mars's orbit is definitely noticeable. You'll notice the gap here between the Earth's orbit is significantly bigger over here and significantly smaller over here. So Mars is on an orbit that is elliptical enough that you can actually tell that it's elliptical. But most of the planets like Venus and Earth and Jupiter are on circular orbits. Mercury is also on a very elliptical orbit. In fact, if we ignore Pluto, Mercury has the most elliptical orbit of any planet in the solar system. Pluto's is even more elliptical than Mercury's. But the bodies that have really elliptical orbits are the comets. So here's an example of Comet Encke right here. So Comet Encke orbits the sun on an ellipse with a very high eccentricity. But there are some that are even much higher than that. Here's Comet Kopff, and then finally Halley's Comet, the famous Halley's Comet. Halley's Comet orbits on an ellipse whose eccentricity is greater than 0.9. In fact, it's 0.967. Here is a plot of the eccentricity of Halley's Comet. At its closest, Halley's Comet is about the same distance from the sun as Mercury is, and at its farthest, it's way out there beyond the orbit of Neptune. The sun sits at one focus, the other focus is empty. But you can see this is a very elliptical ellipse, and that's why its eccentricity is so high, 0.967. If a body is orbiting the sun, Kepler told us that it's orbiting on an ellipse. If a body is traveling too fast to get caught by the gravity of the sun, it will swing through the solar system on an orbit that is a parabola. So there are three types of orbits. There are ellipses, if you are bound to the sun. So imagine that the sun right here. And what we mean by bound is that you're moving slow enough that gravity can capture you. Then you will orbit the sun in an ellipse. If you're traveling at just the right speed to be barely bound to the sun, you're traveling on a parabola, and that's a very special class of orbits. And if you're traveling faster than that, you travel on a hyperbola. Well, interesting, in the last few years, for the first time in human history, astronomers have discovered two different objects that went through our solar system on hyperbolic orbits, orbits that are hyperbolas. And that means that neither of these objects belong to our sun. They were interstellar interlopers. The first of these is called Oumuamua. And Oumuamua came through our solar system in 2017, came close to the sun, and then was also on a highly tilted orbit and came out of the solar system that way. But it was on a hyperbolic orbit. It was on an orbit that does not close, which meant that Oumuamua came from a distant solar system. We believe it was a rocky or possibly even a metallic asteroid, very, very flat, spinning around as it passed through our solar system. The second object that was recently discovered in 2019 is called Comet Borisov. Borisov was the first person to observe the comet, and it's also traveling through the solar system on an on a hyperbolic orbit. All right. So those are just sort of interesting things that don't orbit on ellipses because they're not bound to the sun. They're literally traveling through our solar system and going out the other side. So let's talk about Kepler's second law. I'm going to read Kepler's second law as he wrote it, but I'm going to give you a better way in a minute to remember it. So Kepler's second law says this: the straight line joining a planet and the sun sweeps out equal areas of space in equal intervals of time. So here's what Kepler meant. Imagine that we have a planet orbiting the sun on an ellipse, and we take the line between the planet and the sun. And as the planet moves around the sun, that line sweeps out an area. And what Kepler said is that if we take an equal amount of time, say 1 month in this case and 1 month in that case, in this case, the planet is moving faster and will sweep out the same area that the planet sweeps out in this one. That is, the planet has to be moving faster here because in that 1 month, it has to sweep out a wider area because the triangle's not as tall. And because this triangle is very tall right here, it does not have to move very fast to sweep out that same area that it swept out here. So the area of this triangle is the same as the area of that triangle. And they're the same because although this one is short, it's very wide. And although this one is very narrow, it's very tall. So both of those triangles have the same area. Here's a better way to put Kepler's law. Kepler's law simply means that if a planet is orbiting the sun in an ellipse, when it is closest to the sun, it's moving fastest, and when it's farthest from the sun, it's moving slowest. So here's a little movie that I'm going to show you that demonstrates exactly this. So there is a planet orbiting the sun. I apologize. I would not, if I had made this movie, I would not have made it look like the Earth, because that little blue and white ball looks so much like the Earth. I don't want to create the misconception that the Earth's orbit is this elliptical. It is not. I wish they had done something else. But in any case, on to the movie. So let me reset the movie here. All right. So you will notice that the planet is moving faster here because the triangles are not very tall. It has to be moving fast so that the area of this triangle can be the same as the area of these tall but narrow triangles right here. So you'll notice how slowly the planet was moving out here and how quickly it moves as it comes closer to the sun. So I think a better way to phrase Kepler's second law is that a body moves faster when it's closer to the sun. So Kepler's second law, the straight line joining a planet and the sun sweep out equal areas of space in equal intervals of time. I think a better way to say it is simply that a planet moves faster when it's closer to the sun and it moves slower when it's farther from the sun. And you might say, well, why didn't Kepler just say that? Why did he use this crazy equal areas thing? Well, Kepler wanted to know how much faster it's moving here and how much slower it's moving out here. And it turns out that is proportional to the areas of the triangles. And so that's why Kepler did this triangle thing, because that allowed him to calculate how much faster it's moving here and how much slower it's moving here. For our purposes, we just want to know that it's moving slower when it's farther from the sun and moving faster when it's closer to the sun. Here's a fantastic little animation of the orbit of Halley's Comet around the sun. So there's Halley's Comet, and look at how fast it whips around the sun. And then when it gets far from the sun, it slows down and moves very, very slowly. And then as it falls back in, it whips around the sun. And then when it gets far away, it slows down again. So that is the orbit of Halley's Comet. To put some numbers to that, let's go back to this diagram I showed you a second ago. So I was fortunate enough to get to see Halley's Comet in 1986. I was an undergraduate student at the University of Illinois in 1986, so I used not only my own telescope to see it, but I used the big telescope at the University of Illinois to see it. And then in 1987, Halley's Comet was there, in 88, 89, 90, and as it pulled away from the sun, you'll notice it is now going slower and slower and slower and slower. In fact, Halley's Comet is still not at its farthest point from the sun. It's going to reach that point in 2024, and then it's going to start falling back to the inner solar system, where it will make another close approach to the inner solar system in 2061. So you will get to see Halley's Comet in 2061. But what's fascinating is look at how slow Halley's Comet moves out here. Maybe another way to put it is this was 1985, 1986, 1987. In 2 years, Halley's Comet went all the way from being out near the orbit of Jupiter to passing close to the sun to being out near the orbit of Jupiter. And out here, it's going to spend from 2010 to 2040, 30 years completing that little tiny bit of its orbit out there. So just to sum up, planets move much faster when they're closer to the sun and much slower when they're farther from the sun. That is Kepler's second law. Kepler's third law says that the squares of the planet's periods of revolution are in direct proportion to the cubes of the semi-major axes of their orbits. And that's a tough one to digest right there. So let's talk about two things. Let's talk about a period of revolution. What he means by that is how long it takes the planet to orbit the sun. And we measure the periods of revolution in years. It's how many years it takes the planet to orbit the sun. So in the case of the Earth's orbit around the sun, it's really easy. The period is exactly 1 year. In the case of Jupiter, the period is a little bit less than 12 years. In the case of Saturn, it's about 29 years. In the case of Pluto, it's 248 years. That's what we mean by the period of revolution. The semi-major axis, you already know from earlier in this lecture, is simply the average distance from the planet to the sun. So we could just substitute the word here, average distance. And what Kepler is saying here is that the square of the period is equal to the cube of the distance from the sun. So let's put this in an equation. And this actually shows why scientists use equations all the time. We use equations because they are a shorthand, simple way to say something that's actually quite a mouthful. It's really quite difficult to say otherwise. So Kepler's third law can be expressed like this, that the distance, the average distance from the planet to the sun cubed, is equal to the orbital period, how long it takes to go around squared, if, and this is a big important if, and you should outline this in your notes, you should write this down in your notes, if the distance is measured in astronomical units and the period is measured in years. P has to be measured in years, A has to be measured in astronomical units. So A cubed is equal to the period squared, P squared. So let's do a trivial example here. Let's do the Earth. What is the period of the Earth around the sun? Well, I already said it was 1 year, so the period is 1. What is the average distance from the Earth to the sun measured in astronomical units? Well, that's the definition of an astronomical unit. An astronomical unit is the average distance from the Earth to the sun, so A is 1. So let's plug the numbers in for the case of the Earth. In the case of the Earth, the semi-major axis of the Earth's orbit is 1 astronomical unit, and its period is 1 year. Therefore, when we plug the numbers in, 1 cubed, the distance cubed, is equal to 1 squared, the period squared, right? The distance cubed, 1 cubed is 1 times 1 times 1, which is 1, and the period squared is 1 times 1, which is 1. That's a trivial example. Let's do a more interesting one. Let's talk about Mars. The semi-major axis of Mars's orbit around the sun is 1.5 astronomical units. It's 1.5 times further from the sun than we are. Its period is 1.88 years. So now let's plug those numbers in. You can do this in your calculator to check it if you want. 1.52 cubed, the distance cubed, must be equal to the period squared. The period is measured in years. The distance is measured in astronomical units. If you plug 1.52 times 1.52 times 1.52, put that in your calculator, you get 3.53. And 1.88 squared is also 3.53. So we've confirmed that the two of these are the same. Now here's the silly thing. Astronomers don't usually do that. We don't go around measuring the period and the distance and then cubing the distance and squaring the period to make sure that Kepler was right. Typically what it means is that if we measure one of them, we can measure the other one. So let me give you an example with Jupiter here. What is the distance of Jupiter from the Sun if its period is 11.86 years? Well, if we know the period, we can get the distance through Kepler's law. Now, to do that, we know that the distance cubed is the period squared. So let's take our 11.86 and square it. So the period squared is 11.86 squared, which is 140.7. And therefore, the average distance of Jupiter from the Sun is the cube root of 140.7, 140.66. And that is 5.2. Since 5.2 cubed is 140.7, or the cube root of 140.7 is 5.2. Here's an important thing. For some homework problems, and absolutely on the upcoming quiz and the final exam, you're going to do some Kepler's laws problems like this. You need to know on your calculator how to take a cube root. So let's do this for Halley's Comet so that I can show you on at least one calculator how to take a cube root, but you need to figure this out on your own calculator, okay? So Halley's Comet takes 76 years to orbit the Sun. What is its average distance from the Sun? So let's work it out on the calculator. So let me bring up here the Microsoft calculator, bring it over here where you can see the Microsoft calculator, and just remind you of the problem. And the problem here says that Halley's Comet takes 76 years to orbit the Sun. What is its average distance from the Sun? Well, you'll remember that the semi-major axis cubed is the period squared. If the period is 76 years, we need to square that. And 76 years is 5,776. Now, the semi-major axis is the cube root of that. So how do we take the cube root? Well, on the Microsoft calculator, you take second. And you'll notice now that these functions over here all changed. There used to be x squared and x cubed and x raised up to the y. But when we do second function, we now take square root, cubed root, and then some arbitrary root. So let's take the cubed root of 5,776, and we get 17.9 astronomical units. And that is the average distance of Halley's Comet from the Sun. That is the semi-major axis. The major axis is almost 36 astronomical units, right? It's 17.9 squared, so it's 35.8. Well, Neptune is about 30 astronomical units from the Sun, and that puts Halley's Comet way beyond Neptune when it is at its farthest from the Sun. So this is how astronomers typically use Kepler's third law. It allows you to determine the semi-major axis of the orbit if you know the period, or the period if you know the semi-major axis. So let's put this to work. In 2005, if I remember correctly, an astronomer by the name of Michael Brown at Caltech discovered a new body orbiting far out in our solar system. And the name of that body is Eris. And Eris was almost the same size as Pluto. And the way they discovered the body is it was moving around the Sun. So here's an image, actually looks very much like the images that you can take with the Rapid Response Robotic Telescope. And here's a little object that you will notice that's not sitting still, but it's slowly moving. And in fact, I recommend that one of the things you can do with the Rapid Response Robotic Telescope is you can take a picture of an asteroid and go back a few hours later and take a picture of the asteroid, and you will see that it's moved. If you come back a few days later, you'll see that it has moved a lot. And so the fact that as they were photographing parts of the sky and they saw something slowly moving through the sky, that's an indication that it's something orbiting the Sun. From measurements that they made of its motion, they determined that this object was way out beyond Pluto. Here's the orbit of, in fact, so here's our Sun. There's the orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto. And this is the orbit of UB313, now called Eris. And this is a photograph of what it looks like. So there's Pluto and its moon Charon. Here's a couple of these other Kuiper Belt objects. This one has a moon. And here is Eris with its moon, now called Dysnomia. So the orbit of Eris has a semi-major axis of 68 astronomical units. How long does it take Eris to orbit the sun? So go into learning catalytics and answer this question. How long does it take Eris to orbit the sun? All right, welcome back. So how do you go about answering this question here? Well, we use Kepler's law. The semi-major axis, the average distance cubed, is equal to the period squared. So the period squared is the semi-major axis cubed. The period squared is the semi-major axis, which is 68 astronomical units cubed. 68 cubed is 314,432. So again, you can just plug that into the calculator here. 68 cubed is 314,432. Well, the period is the square root of that. So the period is 561 years. So that is the period of Eris around the sun. Eris takes 561 years to orbit the sun one time. Now, one consequence of Kepler's third law, that the period squared is equal to the distance cubed, is the planets that are closer to the sun and they have smaller distances also have smaller periods. So the planets that are closest to the sun take the least amount of time to orbit, and the planets that are farthest from the sun take the longest time to orbit. So these are just some of the properties of the planets. Do not memorize this table. I would not ask you what is Saturn's average distance from the sun or Saturn's orbital period. If you need these, you can look them up. Or on the quiz, I will give you any numbers that you need. But here are some things. So Mercury is about 0.4 astronomical units from the sun. Venus is about 0.7, and the Earth, of course, is 1. Mars is 1.5. Jupiter's 5.2. Saturn's 9.5. Uranus is about 19. Neptune's about 30, and Pluto's a little bit less than 40. And here's their orbital period. The period, we normally measure it in years. In the case of Mercury, I will tell you that it's 88 days, and Venus is 224 days. That's better than just showing you a decimal year. But for Kepler's laws, we have to convert those to years by dividing by 365.25. The Earth, of course, is one period is 1 year. Mars is 1.88 years. Jupiter takes a little less than 12 years to orbit the sun. Saturn takes a little bit less than 30 years to orbit the sun. Uranus is about 84 years to orbit the sun. Neptune is 164 years to orbit the sun. Neptune has completed one orbit around the sun since the time that it was discovered, way back in 1831, if I remember correctly. And then Pluto was discovered in 1930. It hasn't completed even close to one orbit yet because it takes 248 years to orbit the sun one time. So Kepler discovered his laws of planetary motion, his 3 laws of planetary motion. Every planet orbits the sun in an ellipse with the sun at one focus and the other focus empty. His second law says that things move faster when they're closer to the sun and slower when they're farther away. And then he discovered the period semi-major axis relationship, how the orbital period depended on the distance from the sun. Kepler felt that underneath all these rules, there must be a deeper, more profound explanation. And this is something that scientists do all the time. Scientists are constantly searching for deeper explanations behind the phenomenon that we observe in the universe, because ultimately it is that explanation that provides us new information about the universe. So Kepler felt that there must be some explanation for his equations. So he tried lots of things. He thought that it might have to do with musical notes. He called it the music of the spheres. Then he thought, well, maybe it has to do with perfect solids. There are only a certain number of perfect solids. And maybe it has to do with planets being nestled one inside the other with perfect solids. Ultimately, Kepler was never able to come up with a description of why his laws worked, just that they did. The description as to why, the explanation as to why they work, comes later with Isaac Newton, and we're going to meet him in our next lecture. But I very briefly want to take an aside here, outside of astronomy, and talk about the difference between theories and laws. I think it's a really important thing that everyone should understand, and I think most people have a very incomplete understanding of theories and laws. So since we're starting to introduce the ideas of theories and laws, I thought now was a great time to do it. I want you to go into learning catalytics, and I want you to describe a law. So go in, just use a word cloud, just type a couple keywords that describe a law in science. What is a law in science? All right. We'll come back to what the definition for a law is in a second, but now I want you to go in. How would you describe a theory? In science, what is a theory? So go ahead and answer that in learning catalytics. All right, finally, I want you to answer this question. What is the relationship between laws and theories in science? So go to Learning Catalytics. Again, spend a minute, answer this question. What is the relationship between laws and theories in science? All right, so we'll talk about all those in a minute here. I think the best way to start understanding what theories and laws are is to just list some. So here's a list of theories on the left and laws on the right. So let's start with the laws. Newton's second law of motion. We'll see this in our next lecture when we talk about Isaac Newton. But Newton's second law of motion, it describes the relationship between force and mass and acceleration. That is, if I have a certain mass and I apply a force to it, it tells me what the acceleration is. Or if I want a certain acceleration and I know the mass of the object, it tells me what force is required. And then there's the ideal gas law. The pressure times the volume of a gas is equal to a number, the density of the gas, times a constant, times the temperature of the gas. PV is equal to nRT. And it describes the relationship between pressure and volume, temperature, and density of a gas. In biology, there is the law of independent assortment, and it describes the principle that traits are passed on to offspring independent of each other. And then finally, in geology, there's the law of superposition that says when you look at a whole series of rocks, the ones on the top are younger and the rocks on the bottom are older. And that's because of the way rocks get laid down in sedimentary layers. Generally, unless there's a very violent event, rock layers don't get turned over. And so generally on top are younger rocks and on the bottom are older rocks. Now let's look at some theories over here on the left side. There's the theory of plate tectonics. It says that Earth's crust is divided into plates that move. It explains why earthquakes and volcanoes occur in certain zones around the world. The kinetic molecular theory. Matter consists of tiny particles in constant motion whose speed is proportional to their temperature. It explains the gas laws. And then germ theory. Contagious diseases are caused by indivisible microorganisms. It explains the causes of many illnesses. And atomic theory says that all matter is composed of elements, little indestructible elements called atoms, and it explains why matter is conserved in chemical reactions, amongst many other things. So what's the difference between laws and theories? Here's what the difference is. Laws describe and theories explain. Laws and theories are two different things. Laws describe and theories provide an explanation. And the reason that it's important to understand this is because you may have said, because many people often do say, that theories are tentative, and eventually, after they're proven well enough, they become laws. And that is not how scientists use the term theories and laws altogether. That might be how we use it in our everyday life, right? Laws are absolute. They're never broken. They're not, well, you can break the law, but you're not supposed to, right? Laws are absolute. The speed limit is 55 miles an hour. If you go faster than 55 miles an hour, even if it's just a little bit faster, you're breaking the law. Laws are absolute. Theories, on the other hand, in everyday use means, I'm not so sure, right? My theory is that the butler murdered the plumber, or murdered, I can't remember clue now. The clue just popped out of my head. Professor Plum in the dining room or whatever it was, right? The butler did it as a theory. I'm not really sure. It's my idea. Scientists don't use theories and laws that way at all. So let's talk about how scientists use them. A scientific law is an observed and tested generalization that describes a pattern in nature. Laws describe. They describe patterns in nature. Very often, a law takes the form of a mathematical expression, like Newton's second law or the ideal gas law, but it doesn't always take the form of a mathematical expression. Laws are generally true, but all laws have exceptions. So that's an interesting thing. A belief amongst the public is that theories evolve to become laws, that laws are somehow better than theories. But it turns out laws are not exact. Let's take the ideal gas law. What kind of gas does the ideal gas law apply to? It's not a trick question. It's an ideal gas. How many ideal gases are there in the universe? And the answer is easy. There's exactly none. There are no ideal gases in the universe at all. So the ideal gas law, in fact, so the argument here is that the ideal gas law, although it works, and it works very, very well, it is not exact. There is no ideal gas that it actually holds for. So all laws have exceptions. Laws are not absolute. In science, a scientific theory is a general principle supported by a substantial body of evidence offered to provide an explanation of observed facts and as a basis for future discussion and observation. But here's things about theories. A theory in science is supported by a substantial body of evidence, and it provides an explanation. So when we talk about the theory of evolution, we're talking about a general principle that is supported by a substantial body of evidence. We don't use the word theory with evolution because we're not sure about it. We use the word theory because we're absolutely sure about it because it is supported by a substantial body of evidence. The most powerful theories out there are ones that account for new data and consequently predict new phenomena that weren't thought of at the time. So if you develop a theory, an explanation for what's going on, and it explains things that you never even thought about, that's a very powerful piece of evidence that you might be on the right track. Theories, like laws, are not absolute. All right, so you may have learned in high school that there is sort of this hierarchy that facts lead us to developing hypotheses, which become theories, but when they're supported, so hypotheses, when supported by experiments, become theories, and eventually when they're proven, they become laws. It turns out this is not how science works at all. Theories do not become laws. They're two different things. Laws describe and theories explain. In fact, the major flaw in this idea that theories become laws is typically the laws are discovered first. Let's go back to this theories and laws for a second. The gas laws, Boyle's law, the ideal gas law, these gas laws were discovered back in the 16th, 17th, and 18th century. They're quite old. But atomic theory, the kinetic molecular theory. The kinetic molecular theory, which explains the gas laws, wasn't developed until the early 20th century. It's not that theories become laws. It's that the laws are found first and they describe what's going on. And then later on, we're able to use those laws to come up with an explanation, and that explanation becomes the theory. So Kepler's laws describe, and you can use Kepler's law to think about what each one of them describes. So what does Kepler's first law describe? What does his second law describe? What does his third law describe? Go back, review Kepler's 3 laws, and figure out what each one of them is describing. But just keep in mind that theories do not become laws. All right. That's all I have for this lecture. I will see you in the next lecture where we will meet Isaac Newton and his law of gravity. And it turns out that Isaac Newton's laws of motion and his laws of gravity provide the theory, the explanation behind Kepler's laws of planetary motion. I will see you then.